One of my favorite topics, or at least starting the topic and getting us towards there, are tree-based models. So today is going to be decision trees. Possibly we'll talk a little bit about the beginnings of random forest. I'm assuming I'm not going to get through all the material today. I prepared all of the tree models and they're in these slides, but I'm definitely expecting them to be broken into two classes. So the way that we're going to think that you should think about this is that decision trees are the basis of, or the building blocks of random forest and of gradient boosted trees. I would say 50 to 75% of the time, probably 75% of the time, when I go through all of the models, when I do feature selection and tune models, unless you go to deep learning, either random forest or gradient boosted trees is almost always your top model, usually gradient boosted trees. They, in general, out of the box, are really effective and do, even without very much tuning, really get high accuracy levels. And as we go through it, you'll understand more as well. Another awesome thing about them is they automatically export feature importance. So when we're actually going in and trying to narrow down which variables should go in our model, these are the best options you have. They're processing intensive, so I will not be running the code live. I've run it prior to this class, and we'll be going through the results. So decision trees are the basis of those two models I just talked about, random forest and gradient boosted trees. We basically take thousands of decision trees and use them. So I'm going to talk about the decision trees first and then move on. A decision tree model is a classification model. There is a classification model, as you probably already know, is predicting a categorical value. There is a version for predicting continuous values as well. So we'll go over that today, but they are extremely similar. But we're going to start off with the classification model. It splits your data into progressively smaller groups in something that looks like this tree diagram here. And I'm going to zoom in. I try to stay outside of full screen mode so I can go between code and slides. But you can see here, this is just a small example of what a decision tree may look like, predicting whether I should accept a job offer. The salary, at least $50,000, and that would be the first node. And then you would go down the trees, and as you answer questions, it's going to split off pieces of your data into those smaller groups until we get to the last nodes here. This tends to be great with stakeholders who don't trust machine learning and data science. It's very helpful because you could show them the actual tree and show them where the cutoffs are, and they would be able to intuitively understand it. However, unfortunately, there's some problems with with decision trees that alone make them not as useful. But you can think of it as a series of yes or no questions that predicts a value. All right. So to talk a little bit about the tree structure itself. So what up at the top, the very first node is called the root node. So that's where you start on the tree. I often look at these and kind of think of genealogical diagrams. They remind me of those. And then everything after that, until you get to the final bottom group of nodes, are decision nodes. So those are the ones that are going to where the data flows, and it's going to split your data into progressively smaller groups. And finally, the leaf nodes or terminal nodes, you'll hear them interchangeably when you read about this, are the actual predictions. So once you've gone through all the questions, it's going to dump you out on one of these leaf nodes. And the example here is accepting a job offer or declining a job offer. But in our case, we're going to be showing an example of predicting readmissions to substance abuse treatment. That's the one that I've been using going forward in this class. So this is very intuitive. Stakeholders can understand it. So it's very helpful in that way. So before I go on to more detail, at a high level, are there any questions? I am going to cover how you know how to make the different splits and how the model chooses those splits in a moment. Okay. So the model continues to split your data, and it stops for one of three reasons. One, there are no more, everything has come down and there are only one value in your different leaf nodes. There are no remaining features to split on, or when you're hyperparameter tuning or tuning your model, you sometimes predefine a stopping criteria or an early stopping criteria. You might have heard that before. That is the most common reason to stop a decision tree. In general, decision trees are not great because they overfit. So you usually have to do this third option or it's going to not be a very accurate model. We'll get more into that in a second. But with any tree-based model, there is one difference between this model and other models that you might have seen me go over, or pretty much any other machine learning model. So often you're told to a dummy code your categorical variables, and you are told to rescale your continuous values. It's actually better not to do this with any tree-based model. So decision trees, random forest, or gradient boosted trees. There's always, I got this question from someone I work with that I'm trying to teach him machine learning. And he actually had a really great question about this. So he's building a pipeline and he's trying a lot of different models. He said, so do I make a whole new data set just for the tree-based models? And that's something that you might have to weigh. The answer I gave him was, I usually see good performance either way with using dummy coding and it not rescaling or rescaling for tree-based models. I'm like, you have to weigh how much extra effort it is to just have a whole different data set for this versus the alternative. I usually, in a lot of cases, have just, even though it's not the best possible model we can have, went with the dummy coding and the rescaling because every other model that I try has that already. So if you're building a pipeline and say you're building an automated pipeline and you want to retrain your model and pick a new model every time, it's not feasible to use two different data sets. So you're going to come across a lot of these things as a data scientist where you're like, okay, it's best practice to do this, but there are logistical reasons why it might not be the best option. And you always have to weigh the positives and the negatives there. So your model will actually do better though if you do not do those things because it is not distance based like the rest of the models. That's the difference. K nearest neighbors, SVMs or support vector machines, all of those have some element of distance or gradient descent involved, which mean that everything has to be on the same scale, but that is not the case here. Are there any questions about that? Awesome. And I can see the chat, so feel free to ask anything in there. I should be able to hear it. Or also unmuting your mic. So this is the heart of decision trees. I mean, it has to choose the best split in order to give you the best prediction. So the crux of all of this is understanding how the model does that. And once you do that, you pretty much understand decision trees. So just like every other model that you've seen, there are multiple ways to do this. And I'm going to show you first the most common. The most common is looking at information gain. Either way, you're always looking at those splits that give you the most information gain. There are different ways to measure information gain. The most common one is to look at Gini impurity. It has a specific formula that I'll go over in a second. Another common one is entropy, and they, in practice, usually yield pretty similar results. So this is one of those hyperparameters with a tree-based model that you can try multiple values and see if the accuracy increases or decreases in your use case. Gini impurity talks about basically how much information you get, or how the variety in your groups is coming out. So it's easier to just talk about the formula. So we want to look at our different groups. Say we have one group here, and I'm using very simple, and then I'll explain it in the context of machine learning. But say we have a group of balls, blue balls and black balls. We have 6 blue balls and 4 black balls. In order to get the Gini impurity, we have to first put our blue cap on and say, okay, if I'm looking for a blue ball, what are the chances, the probability that I will choose incorrectly or I'll misclassify? So in this case, that's 4/10. And you can see that that likelihood is here. And now we want to put on our black ball cap and say, what is the chance, if I'm looking for a black ball, that I will pick up a blue ball by accident? So that, in this case, since there's 4, there's a 6 out of 10 chance that I will get that wrong. And simply Gini impurity is multiplying those two numbers. So it would be 4/10 times 6/10, and our Gini impurity would be 24/100. So you would repeat this process. Say you had 3 different categories. You would do it for the 3 categories. I'm showing 2 here because in general classification problems, the most common you're going to see is a binary. But that's the great thing about decision trees and tree-based models, is they can handle multiple, more than 2 categories. You don't have to do anything special for those. So that helps as well. Some models you have to train many models to look at more than 2 categories. So in this case, 0.48 is our Gini impurity. In general, it ranges from 0 to 0.5. So obviously this is a very bad Gini impurity. We are guessing wrong a lot. 0 would be, it's all one color in our group. And 0.5 would be, there is equal chance of getting it wrong in both classification groups. So that's Gini impurity. Are there any questions?
Yes, I have a question. What happens if the blue and black, you're assuming this is a binary data? Like, what if this is a continuous feature?
Yes, so that I'm going to go over all of the classification part of it first, and then I'm going to come back to regression trees and circle back to that. So hold that question, and we'll talk about that in a couple slides down the line. Okay, it's very similar, so I just want to get this one out of the way, but because it's more simple, and then I'll get to that part.
Thank you.
No problem. So in the context of machine learning, so going from this colored ball example, in the case of an actual machine learning model, it would be, in our example that I'm going to show in the code in a minute, whether a substance abuse admission is a first admission or a repeat admission. You could think of it in the same way. So the model's going to go through many different splits. So it's going to try and test out a lot of different ones. It's going to find the one that for that step, it increases information gain by the most. And then in the next step, it's going to do it again. And it's going to find for those two remaining groups, which split will give us the most information gain. And it will keep going until it hits that stopping criteria or runs out of features, or there is one value in each leaf node. So another example here, I wanted to give kind of two so that there would be two examples and hopefully you would understand a little bit more about it. So here's a second example, predicting whether you're going to fall based on how slippery a floor is and how slippery the grip on your shoes is. So this is a little closer to our machine learning example. It adds in basically our two predicted variables. So in reality, you're going to have way more than two predictors. But in this case, you can see shoe slipperiness here that goes from 0 to 4, floor slipperiness here from 0 to 4. So, and then it basically, as this example shows, just plotted them for us. So we could try to understand what the model would do in practice if we had this very simple example. So in this case, the highest information gain is going to be where this red line is. It would have tried here, it would have tried here, it would have tried multiple places to see if it could look for the best cut. So in this case, we on this side are getting it wrong one time. On this side, it's actually half and half. This is very common. When you're doing machine learning, I almost always notice that almost every model gets one side wrong a lot more than the other side. There's a lot of ways to deal with that, and that'll be something that actually this deals with it well, and I'll talk a little bit more about ways to handle that because you're going to see it in almost every model you ever build. So now I'm going to talk about how we would calculate Gini impurity for this. So in this particular case, we would have a starting impurity. So because remember, we're doing information gain. So we have a starting impurity value, and then we want to get the most information gain on that next node. So it will evaluate. So we want to see where that information gain increases the most. So we have to look at the baseline in a real model. If you look at this square as a whole, 19 out of 25 times, you're going to have a chance of selecting no fall. And 6 out of 25 times, you have a chance of misclassifying as a fall. So you're going to take those and multiply them together. So that's one side of our decision tree. And then the other side is if you're trying to select a fall, there is again, 6 out of 25 chance of misclassifying on one side and 19 out of 25 chance of misclassifying on the other side. By the sides, I'm actually referring to on one side of the red line and on the other side of the red line. So, but right now we're looking at everything as a whole. And now the total before we're doing any splits, our Gini impurity is 228 over 625 or 0.36. That's where we're starting as a whole. So that's we can think of as our baseline. So now we're going to look at the split that they're actually making. So a group above 0.15, 1.5, and the group below 1.5. So 0, this is small, so 0 is down here. So this is the group below 1.5. That group below 1.5, there's a 5 out of 10 chance of selecting no fall and getting a misclassification. And if you flip it around, there's a 5 out of 10 chance of accidentally classifying a fall as no fall. So multiplying them together, we get 1/2, 0.5, or 50 out of 100. The other side of the split, we have, it's much better. We're getting it right more often. So in this case, we're getting it right 1 divided by 15 times when we're looking at or trying to select no fall, and we would get the wrong label once. And then when we're trying to select fall, we would get the wrong label. You basically just flip it. And you would get that 1 out of 15 times. So I actually misspoke there. The top, getting no fall, we're going to misclassify 14 out of 15 times, excuse me. And then for a fall, you're going to get the wrong label 1 out of 15 times, which you're just basically turning them around. And that would be 14 divided by 15 times 1 divided by 15. And then we have now the information gain here. So for the group above 1.5. Finally, to get the overall information gain for the entire split, we take the total number of data points, which is 25. The group above 1.5 has 15 data points. So we actually do a weighted average here. You can think of it exactly like that. So this was our Gini impurity for one side. This was our Gini impurity for the other side. And we weighted them by how many points were on this side of the line and how many points were on this side of the line. So our weighted average comes out to a Gini impurity of 0.27. So now we can see our original Gini impurity with the whole box was 0.36 and minus 0.72, we would have a Gini impurity of 0.09. So it is going to do this for most of the potential splits in your model. It's going to try a lot of different options. The data scientist actually controls some of those options and decisions that the model makes. That's going to be the part that's the most, I would say, challenging of this class today, is the tuning part of this model. Are there any questions about Gini impurity? All right. So entropy is the other option that you do. I'm not going to go over this one in as much detail. But it, instead of actually doing a multiplication and looking at a misclassification, entropy is a measure of disorder. So it actually has a mathematical formula. It usually ranges from 0 to 1. An entropy of 1 means that all observations are in the same class. Closer to 1 is the higher level of disorder. In this case, we have a similar thing. So if we have those 6 balls, blue balls, and 4 black balls, we're just going to put it through this particular formula up here. So we would take and you always have a negative in front, the 4 out of 10 for the black, and we would multiply that by log base 2, 4 out of 10. And then we would subtract for the 6 out of 10 times log base 2, 6 out of 10. And then you would just calculate that out. And the entropy in this case would be 0.97. And you would always, just like in the other example, look at the base information gain and then look at how much it changed in a real life example. So I'm going to go on now to regression trees. So the question that I got about how do you do this with a continuous variable, this is how you deal with that. So what we just talked about is taking a class and predicting a class. I am switching gears to predicting a numeric variable. Example that I used in one of my jobs was like predicting corn yield. That would be a good example of a regression tree versus a classification. So as we said, decision trees are for classification models. Regression trees are built in a similar way to decision trees, but the splits are evaluated on things that you've probably heard before. This is going to be it's going to be easier for you to understand. They are evaluated on the change in variance, the change in standard deviation, or the absolute deviation from the mean. So we would look at the node up here and see how much the variance it changes when it goes to the next row. That probably makes intuitive sense to you guys. And when we look at the predicted value, this was actually the question that was asked. So when we have our final nodes for classification, you just take the majority value that shows up in that final leaf node. Here, to get a prediction, you actually find the mean of everything in that final leaf node, and that gives you your prediction. So that's how a regression tree would be different from a classification tree. There are actually two options. So you can actually do this with regression trees, where you do everything the same as a decision tree, except the split differences are different because you're looking at variance, standard deviation, or absolute deviation from the mean. You can also actually make each node a linear regression. That is the thing that happens and people use. I'm not going to go over that today, but know that that is an option as well. This is more just looking at the information gain, just like the classification model did. Are there any questions about this one?
Yes, I feel like I'm missing something. Let's say that we have a dummy feature, okay, and the dummy feature has a very large variance, but it provides no information. We are still, according to this, we are going to use this dummy feature to split the tree, right? Because it has the biggest variance, but that doesn't provide any valuable information.
So we would, again, have our full box. The difference here is it wouldn't be predicting yes or no, or a classification. So we would look at the variance at the very start. And the whole group, it's going to be really large. So obviously, we're going to see a big difference. Then for each individual split, so we would have our baseline variance, and then it would try different splits. The shoe slipperiness above or below 1.5 was our example in classification. But in that case, instead of for each individual split, the model will test out multiple options. It'll make multiple cut points. It will use multiple features. It will try many, many values and many options, which is why it takes so long to run. And then it will see the one that decreases, where the variance decreases the most. So the largest drop in variance of all the many ways that it tried. So it'll try a cut point here. It will try also looking at floor slipperiness and try all of the cut points for that, or most of them. And then when it will try and test them all out and pick that one where the variance drops the most. So basically the one that is making those groups in your nodes more homogeneous or more similar to one another. And theoretically, at the end, you should have leaf nodes that are very similar where the variance is very low at the end. Does that help at all?
A little bit, because when you said variance at the beginning, I thought that we are going to pick which feature to split on based on the variance of that. But it seems to me that you are calculating the variance based on the leaf nodes. So
yes. So you test multiple features. You test multiple cut points within those features. You
evaluate based on the leaf node, not on the root node or the middle nodes.
So you look at the root node and you look at the change between the root node and the next node. So the biggest drop in variance, and you can look at them as groups. So everything together is going to be your root node.
Okay.
And you get the variance there. and then it's going to test different options. The one where the leaf, and they are decision nodes, the next level, where that variance in your two groups drops the most, that's the feature and the cut point that it will do. And that will be the feature in the cut point that allows for the most information gain in that case.
Okay, thank you.
Yeah, so it's actually the nodes that you're looking at, the variance or the standard deviation or the absolute deviation from the mean, but the comparison and the thing that it's testing is
Before
the
and
different
after.
features and the different cut points. Yeah.
Okay, thank you.
Yeah. Thank you for the questions. I absolutely 100% welcome them, because if you have that question, probably somebody else did too. So, are there any other questions before I move on? Don't see anything in the chat, so. Awesome. So we've talked a lot about decision trees, but I want to go in real quick and show this a little bit in the code. I think it will help bring this, and then I can talk a little bit about overfitting, because this is really important, particularly in decision trees. So here, decision trees, I basically had all of my features in here, which this was before I did feature selection, which I did farther down in the code. By the way, if you want to try this, I highly recommend reading the data in here. I kept the data munging steps above it just so you could see what I did, but I took a much smaller sample of the big data set, and you can read that in here. So this is how in Scikit-Learn you would actually run a decision tree classifier. In this case, we are looking at a lot of different characteristics of individuals, and we're trying to predict whether it was a first admission to a substance abuse treatment center or a repeat admission, so 2 or more admissions for that person. And all of the models that we've seen already in this class look very similar to this. Scikit-Learn is very easy to understand. You always want to make sure it's in a NumPy array. I've already gone through the rescaling process. Like I said, you don't have to do that here, but this was part of a much larger model evaluation project. You'll see that every class I have a different type that I'm using. So I did make the decision to do it that way in this case and keep it consistent. So we have our decision tree classifier here. Make sure at the very top you are reading in and loading the packages. Otherwise, you're going to get an error here. We have our training data. First, we basically make the skeleton for the model. You usually want to pick random state and pick any number there. This will just make sure that the randomness, that your model will come out the same every time, because there's a random element to this model. So we make the skeleton, and then we take our training data. So our X training data, so those are our predictors, and then our outcome values, so our known values, and then we fit that decision tree model with our training data. Then we actually use a validation data set to predict that, and then look at the results. So this decision tree is performing very poorly, which you would actually expect, and I'll explain why in a second. So like I said, I haven't done feature selection yet. And I also specified no hyperparameters here. So I did not use early stopping. I'll understand what early stopping, I'll show you what early stopping means in a minute. So I ended up with a terrible accuracy. It's 0.65, so this model isn't much better than chance on predicting readmission. One great thing that I already mentioned, you can output feature importances with any tree-based model. This is fantastic because in general, the best way, if you were looking at the gold standard to do feature selection, is to literally take each feature out and put it back in and look at the prediction difference. This model actually does that inherently as it's running it. It's trying different features and trying other features, and it's looking at the accuracy difference as you go down that tree. So you can output feature importances. I would say this won't be as accurate for a decision tree because you're only running one tree. So I would probably use that later on more often with gradient boosted trees or random forest. So why is this model so bad? We talked about it's going to run until there's one value in each node or you run out of features, since I didn't give any early stopping criteria. Actually, running this takes forever, and I actually cut it off before it finished. So these are all the splits it made. You can see my scroll bar and how it's still going and still going and still going. This tree is massive. So therein lies the problem with decision trees. This thing probably had hundreds of levels, if not 1,000 levels that you're looking in here. So much so that you can't even read this. So that is a classic example of overfitting. I'm going to come back. So since you didn't tell it to stop at a certain point, it is going to overfit that way and just keep going and going and going and training too closely to your training data. So that model will do terribly with the validation data because it will be so closely tailored to your training data, which is why our accuracy was so low. So there are two possibilities for fixing this. One is a lot less common. You can actually go back up and prune your tree. So you can, the computer basically goes back and looks at those splits that really didn't have a very high information gain, and it gets rid of them and it goes up. The more common is early stopping, where you basically set a rule where you stop it at a certain point, and you have the model that you have at that point. There are a lot of different methods for early stopping, and those are the hyperparameters that you tune with these models. So I'm going to go over that in the next slide. Pruning tends to be more effective because it's difficult to judge when you should cut it off. But I don't see it done a lot in practice in general. Early stopping can be done in hyperparameter tuning, and you can try many different models, and that's the way it's usually done in practice. So we've already talked about this to some extent. But this is something to keep in mind as well, and this is why pruning sometimes helps a little bit more. Decision trees are a greedy learner. What that means is when you make a split up here, in reality, you could maybe take a more circuitous route or to get to a better prediction accuracy at the bottom. So your best split at the top might not actually lead you to your best split at the bottom. Basically, it doesn't look ahead. It doesn't look ahead at the most efficient way to do it as a whole. At every step, it finds the most efficient way at that step, and it has no memory of what it did before. And that next split is completely unrelated to everything that it did above. So it makes a new decision each way. Whereas when you use more complex models, it can take into account and learn. So that if it makes the wrong choice up here, it's going to run multiple iterations of these decision trees and find that mistake in more cases by using different numbers of features, things like that. Basically, by the first decision that we make, the decision tree is permanently changed and limited based on that decision, and every decision after that. So it may not have started off at being the most long-term or the best long-term solution, So that is also another reason why decision trees does not perform as well. So the actual modeling part of decision trees, like understanding the model, is not the hard part. So the good thing is all of this is used again when you look at random forest and gradient boosted trees. This is the hardest part of being a data scientist. What I'm showing on this slide is the hyperparameter tuning. You have to know what they do, know what effect it has, and then make intelligent decisions on where to go next. So in this case, hyperparameter tuning, for those of you who haven't had as much experience, are inputs into your models that the data scientist makes a decision on what to put into those models, and it will allow your model to become more accurate or less accurate. We can start with an example. So in general, with tree-based models, I find max depth, I use it almost every time. So it tends to be the most influential hyperparameter that you can tune, and it generally really helps with accuracy. It's the first one I try. So that talks about the maximum depth or the number of levels a tree is based on. So I'm going to go back up to here. So looking at our small decision tree, we have 1 level, 2 levels, 3 levels, 4 levels. There's a depth of 4 here. So that's what max depth is. So you would actually set, in your case for the decision tree, you would say it can't go above 5 levels. It can't go above 7 levels. It can't go above 8 levels. And you would actually try multiple of these. So you would try different max depths. So what this does, so remember a really, really, really long decision tree with maybe thousands of levels. It cuts it off early so that it doesn't overfit. But you have to find the balance here, because if you have really complex data, you need enough levels to parse out the differences in your data, but at the same time, you don't want it to overfit. So I'm going to come in, believe I did max depth first. So I did do here some feature selection. Feature selection is going to probably be included in the next class as well as the class after that. I'm not going to go over that today, but I did do some of that so you would see models that weren't total garbage. So here, I started off with like a base model. You always want to try it with no hyperparameters changed, just to kind of see that base level before you do anything. And we're getting a 6.64 accuracy, so still really, really bad. So in Scikit-Learn, the easiest way usually to do grid search is actually to put it in a for loop. Because you're able to pull out more information along the way. So in this case, I tried multiple max depths. I believe there is a default in Scikit-Learn. I would have to look it up to find out what it is. But I cut it off at 5 levels, 7 levels, 9 levels, 15 levels, and 20 levels. Keep in mind that our data is very complex and it is noisy. So I put in here and I had it change the max depth. I'm not going to run this because this takes a while. Machine learning in general is highly processing intensive. But these are the results that I got. So remember, our base model is 0.64 before we cut it off. Cutting it off at 5, we got a 0.69 accuracy. 7, 0.70, 9, 0.708. Then it starts going down. You'll see this bell curve a lot. So you'll see accuracy be really low at the bottom end of your range or lower. It'll rise, it'll hit a peak, and then it'll go back down. So our sweet spot for max depth was here. It was rising here, it fell here. So it was underfitting on this side, and it was overfitting on this side. So I know if I'm going to choose max depth, and we'll try it in combination with other hyperparameters. If I was going with just max depth, 9 would be our ideal in this case, 9 levels. Are there any questions about max depth and hyperparameters in general? All right. So there's obviously, oh, go ahead. Or a question?
Just to clarify one thing you said, Kelsey, where do you add the hyperparameters in the code? Is it when you're creating the skeleton or when you're fitting?
This skeleton. So you see this decision tree classifier, so that we have that skeleton. I did it dynamically in the for loop though, so I could try multiple and put it into a pandas data frame. So I'm basically using indexing here to pull those different values.
Sure.
And it's dumping them in here. If you use Spark, they have a grid search functionality, which has a lot of problems. It doesn't allow you to even pull out accuracy, unfortunately. But in a lot of languages, they do have something where you wouldn't do a for loop. In Scikit-Learn, there's no parallel processing, so it's just quickest just to do it this way. So we have this here. And of course, got to add more complexity onto it. This is why data scientists make the big bucks, because there's a lot to it. So there are multiple ways to handle overfitting, of course. So max depth is one option, and you can also use it in tandem with other options or alone. Another one that's common is minimum samples per split. I'm going to come back to my handy little example here, where we are showing our different salaries. So basically, if we had the split down here, for instance, so we had 5 samples, say, in this node. If we set the minimum samples per split at 7, it would stop and make this my terminal node. If we set it to 3, it would keep going until any node hit was below that minimum, and it will stop right before that. So it's basically how many data points are in each of your nodes. It can't go below a certain value. One of the questions that you're probably asking is, how do I even know where to start? Scikit-Learn's documentation is incredible. Decision trees. You can see when I was writing this class, I was Googling this. I always have their documentation open. Here's the regressor. I'm going to put classifier here. I'm going to show you this real quick because it's really worth looking at. So always have this open, and you'll see here max depth, the max depth of a tree. If none, then the nodes are expanded until all leaves are pure, or until all leaves contain less than the minimum samples per split samples, which is down here. Sometimes it has a default. In this case, it's 2. So the default, and that often gives you kind of a starting point. So 2 is the minimum here, so you could go up from there. Also, just reading and help in Googling this may help as well. But you can see a pretty clear explanation for most of these in here. I will often do more Googling, but you're going to get a very succinct and clear synopsis always in the documentation. Scikit-Learn is awesome with this. And you can see up here your criterion, Gini versus Entropy. Remember, we talked about that as a hyperparameter. So there are a bunch of different options. This is why trees are so hard, because you can see going down, there's a lot of different options. So we have those minimum samples per split. I tried a lot of different ones here because as we went up, it kept getting better and better and better, and I wanted it to drop off so there could be an example. Sometimes I didn't get it to do that, but in this case, I wanted to show here the default, and up from there. So again, we have our skeleton, the minimum samples per split, which you would get the syntax from this documentation. And we put in 2 to 50, like various numbers between them. Ran that through. I always print what number of the for loop I'm on. So since you're waiting and waiting and waiting and waiting for these to finish, you at least know what iteration of the loop they are on. So you have some idea about how long you're going to be waiting for it to finish. That's just a tip. So here we have really bad for 2. So that's the default, same as the default model at the top. So it's 64. And it goes up and up and up, and it's actually still rising at 50. But at that point, I had been waiting so long, so I didn't keep going. So basically, this model is tending to overfit a lot. That's what it's telling me. So it would keep making that number bigger and bigger. And the best accuracy of the ones I tested was actually 50 in this case, because it prevented that overfitting. So if you were doing this for work, you'd want to keep going until it hit the other side of the curve, so you'd have a better idea of the best one. So that is another example. Any questions about this? Minimum samples per split. All right. Come back to my trusty slides. So the next one, minimum samples per leaf. This is very similar to the one that you saw. So this evaluates the number that is occurring at the split. This looks at the result of the split. So the actual leaves that result after the split. So that's the difference. It's the location of where we're looking at these numbers. So minimum samples per leaf is the minimum number of observations in a final leaf node. So for those final terminal leaf nodes, we can't have below a certain value. So it can't like go down to say 1 observation per node. So that's what the minimum samples per leaf is. And leaf and terminal node are the same thing. So I'm not 100% sure if I used minimum samples. So this one I did not do an example of. I did for most of them, but I figured that they were similar enough that it would be pretty intuitive. This one I'm going to come back to just for in a bit, because this one's the hardest one, but it's also really important. It helps a lot in working with those instances where it's getting the same side wrong all the time. So put a pin in this one. Go on to maximum features. So as you know, it goes and it tries and tests a lot of different features for each individual split. In this case, we're actually putting a cap on the number of features that the model will test, and it will randomly choose. So if you say 7 features, it will randomly choose 7 features to test on each level. So coming back into here, that's the next one I tried. So I would have to go up and see how many features are actually in this data set. Yeah, but I'm not going to go up and go in that diversion. I should have looked before the class started. But I'm trying 5, 7, 9, 12, 15, and 20. Again, you're going to see that similar layout, my max feature value. Ran all 5 iterations. This one in general, I find doesn't change much. You can see that the accuracy was terrible throughout. So it didn't prevent this from overfitting. It didn't do a good job at doing that. So we're seeing almost no difference, and the model's still terrible. You would probably have to use max features in tandem with max depth or minimum samples per leaf or something like that to prevent that overfitting. So this is going to be a good secondary one for decision trees. It's not going to be the one that helps you primarily like stop overfitting. it will help you tune after overfitting is already controlled. So just as I thought, we aren't going to get through everything today. I didn't expect to. So the next time we will be going over the remaining hyperparameters, and these are also all available in random forest and gradient boosted trees, which are the best models outside of neural networks and deep learning that you're going to have a chance to use. So we'll be going over, those are called ensemble methods. So after we're done with the hyperparameters, we'll go over what ensemble methods are, what random forest is, and gradient boosted trees and regressors as well. So those are actually pretty easy to understand once you already understand decision trees. And like I said, 75% of the time, one of gradient boosted trees or random forest is my best model. If I don't use deep learning. So it's definitely worth learning and coming back for. Are there any questions before we wrap up?
Since you mentioned deep learning, Kelsey, just a quick question. Do deep learning models have hyperparameters, since you said that was like the most important decision?
Yes, and they're a lot harder to understand.
Okay.
So that's one. Yeah, so they're way more steeped in calculus, the hyperparameters. So they're a lot harder to intuitively understand. I haven't done a lot of deep learning in my career because usually one of these is sufficient. And I haven't done a lot of image processing or things like that. So I have a couple calculus books upstairs that I've been going through and learning a lot more about that as well. So it's to do it right, it's very steeped in the math, more so than these. So it's harder to understand it without a calculus background, I would say, unless you don't do it right, which a lot of people do it that way. So, yeah. All right. Are there any other questions? All right, I hope this was useful. This is definitely my favorite topic of all of them that I'll cover. So hopefully you enjoyed it. Have a good night, everybody.